We start our the final lecture series. So this is on what is, I guess what the title is kind of, it's complicated, mechanics of wrinkling, folding and crumpling. So this is one of the talks where we'll see real experiments, I guess, and so it's a pleasure to have Narayanan Menon from Amherst giving these lectures.
Thanks. It's on, you can hear me? Okay. So as Abhishek warned you, I'm an experimentalist. So if you were playing Australian rules, we'll be playing with a tennis ball, wickets will be painted on the wall. So this will be low-tech version of how we play. Okay. So here's the thing that I wanted to get across in the next several lectures. If you look around in nature, and I'll show you examples, and in the technological world, you'll see thin objects take on an incredible variety of morphologies. So shape complexity of all kinds you'll see. And I want to try and give you some tools with which to understand those sets of shapes and try and make sense of them as a physicist might. Okay, so here are a few examples. You can see tremendous natural patterning in, say, wrinkle shapes in the world. These are skins of various types. You know this gentleman? You know the gentleman? Okay, so you've been focusing on physics and not watching the World Cup. Very good. He's got a reason to look worried. He's the Brazilian coach. So this is Tite. So you can see incredible patterning here. And here's a bunch in the plant world. These are, that's an orchid of some kind. This is a leaf of some kind or the other. That's a cabbage. And you can see there's a huge wealth of detail over here contained in these patterns. And here are a bunch of inanimate examples. That's fabric. This is just a crushed up piece of tissue paper. This is everyone's favorite material these days, graphene, just sitting on a table. This is a topographic map of another thin thing, the Earth's skin on top of a heavier foundation. Okay. So if you look at these seem to have incredible detail and an incredible amount of information packed into them to generate these patterns. And it's a little bit daunting to think about trying to unpack what is going on here. And for that, I wanted to go back to, the physicist's basic tool. You take a material, you look at it in its most boring ground state. So for these, it might be a chunk of skin and flesh with a piece of skin on top. Look at it in its completely undeformed, highly symmetric state, and then ask, what are the excitations this material has? What kind of basic elementary motifs can you build out of shape like this? Okay, that's the sort of approach we'll take in the next some time, and I want to start looking at these a little bit in not a detailed experiment. This is a leftover piece of material from one of our experiments. Okay, it's a thin piece of plastic. You may see this 3 lectures from now show up again, but this has been through a violent life. And now it's just a discard sample sitting on a microscope slide. And I want you to start looking at some features in here and trying to get some sense of the things we may be talking about. So in some places on this, you can see what looks like a one-dimensional pattern of waves here, here, here. Okay? So these are smooth and small deformations. The deformation is sort of delocalized over a patch of space. It looks like a wave. Has, in some places, what looks like a well-defined wavelength. I'll post everything, by the way. I'll post the slides and I'll post what notes I have. And I'll post some references for you also to look at for later. If you look in other places, you see what you get when we start crumpling pieces of paper. Okay, that's just the schedule. So if you do this, you start seeing sharp patterns like this, right? You'll see folds that run up and down along this material. And you'll see corners where those folds meet. So you see these on your clothes, you see this on your homework. And we'll talk about that class of deformations also. Those are different, those are localized, they're not spread out in space. These are sort of delocalized objects. And finally, in some places, you'll see places where this material is permanently deformed, right? You see these deep lines running, oh, sorry. Yeah, you see these deep lines running across. These are places where the material has either been pinched somewhere or it's got stuck to itself, and it's going to stay there, deformed. We won't talk so much about those. We're going to stay within linear elasticity here. We won't talk so much about plastic deformation, but I want you to understand that the elastic history of this material was important in setting up these. Something made a deep fold before the fold touched itself and did this damage to itself. Okay? So we're going to try and pick out each of these things and talk about them in detail. What may not be so obvious is that all of this fairly recent development, so the basic equations of elasticity are a few hundred years old, but I would say an understanding of wrinkles, folds, ridges, cones is in the last couple of decades. So it's a field that's a little bit on the move. And I want to give you some ways of thinking about each of these in the next few lectures. So I want to point out and emphasize that these structures are generated by instabilities. So we looked at some of these. We looked at the wrinkles, the deep folds, which you couldn't see in 3 dimensions in the last thing, but you can imagine what's going on. You have a piece of material, and instead of smoothly deforming, it tucks in. Ridges you saw, these are decones. This is from the webpage of a person who shows you how to make paper planes. This paper plane happens to be made out of his degree in aeronautical engineering. It's actually a very interesting page. So I'd like to discuss what the energetics are of each of these constructs, how stable they are, and more importantly, I'd like to know if you're applying some general forces and boundary conditions and doing something to this material, when do you see this, when do you see that, when do you see the other, in some unspecified space, as yet unspecified space of, I give you some material, I tell you its properties, I give you some external conditions, and I specify what I'm doing to the material. Where do all these things live? That's what we'd like to get at. And the reason I want to get at that is it's has changed even from an applied point of view. Instabilities in mechanical structures is a deeply well-developed subject in engineering because you want to protect against instabilities, right? So you understand the structural stability of this wall for a very good reason. Okay, you want a clear prediction of under what loading it will fail. That's changed even in the technological world in the last 15, 20 years. I mean, instability is now not seen as a failure, but as a technological tool. You want things that, will respond. You want things that live under unstable conditions. So you want electronics that will be stretchable. You want to use these kinds of instabilities to structure surfaces, make patterns on surfaces. These are not patterns that are made by hand, by scribing lines on a surface. It's made by using one of these pattern forming tricks. So you really want to understand, you want to have control over here. The whole other field which has come a little bit out of the electronic and optical developments, mechanical metamaterials. You want to make materials that have inbuilt places where it will fail, so it will absorb shock or it will change dimensions a lot. or it'll make a waveguide that you can change the band gap off in the middle of its working. This is a ball that's almost spherical, but it can buckle into a smaller sphere. Not easy to make a sphere that can become a much smaller sphere. So this is now really all over in the physics world as well. There are things with interesting topological character, and generally speaking, there's a theme here. People are trying to use low energy excitations that can give you big deviations to change shape a lot. That's the overall theme. Okay, so that's where I want to be at the end of 5-ish days. So this is what I wanted to talk about, and the colors represent my hopes as to when we'll change days. But today, apart from what I just told you, I want to lay out some introductory elasticity. This is, 200-300 years old, but if you were educated as I was educated, you had no elasticity in MSc, Ph.D. Is that correct? You had some? Okay. How many have had elasticity? Okay. So I'm seeing little over a third of the people. Okay. I'm going to go over it quickly today. And those who raise their hands, it's their job to help the folks who didn't raise their hands to sort of fill in the holes here. Okay? So we're going to talk about stress, strain, Hooke's law. Okay, quickly. And then I'm hoping we can get to a place where we reduce to thin elasticity of thin objects today. And I'll talk to you a little bit about a 1D problem, the Euler problem. If we're going really fast today, we'll get here. But then I want to tell you about other 1D problems, instabilities, wrinkling, folds. Then next day we'll talk about two-dimensional problems. And then very large deviation two-dimensional problems. We'll only get to things that are really thermal on day 5 if things are going well. If things are going exceptionally well, we may get there earlier. But let's see how that goes. Okay, so we'll basically travel this path by walking through papers written in the last 10 or 15 years. I think once we're past here, I think these are last 15 years. Okay, here are some things I won't do. By and large, as the topic states, and as Abhishek said, it'll be mainly mechanics. You will not see much statistical physics. Sorry, you can blame them. Okay. There are very beautiful ways to do this subject, which involves laying out a lot of geometry first, upfront, as an initial investment in learning this in a purely geometric way. I will not do that. Otherwise, we won't get to the topics I want to. I will give you a very crude physical engineering approach to the first bit, at least, so that you could get some intuition for what's going on. I said thin things and geometry. Most of what I will work on is sheets. A perfectly good other thing to work on is filaments. Okay? So you could work on long, thin, stringy things which are abundant in nature, and those give you as interesting patterns. Those are as complicated. They give you some things more. You can get additional things that you cannot get in a sheet. You can get torsion in a filament, which you will not in a string. The other way around. For example, your hair will do just as well. He said spider silk. The other sets of things that are intermediate between filaments and sheets are ribbons, where there are 3 scales. You get a thickness which is very small, then a width which is much bigger than that thickness, and then a length which is even bigger than that thickness. There you get other intermediate things. You get other, because there's more length scales. I I hope that what I will tell you will set you up for being able to read these things, but I'll focus on sheets. Sheets have one interesting complication that the others don't, is that if they move in 3 dimensions, they're bound to hit each other finally. So self-avoidance is a bigger problem in thin sheets. Ribbons and filaments can always avoid each other in 3 dimensions. Yeah, please. The question was, what's the difference between a ribbon and a sheet? So let's say there's a width and okay, let's do a width, and let's say that's the length, and there's a thickness. Okay. So I'm going to call this a sheet. Yeah. And I'm going to call this, very bad notation, I'm going to call this a filament. L doesn't look right for this. And no, I'm going to call that I'm going to call a ribbon where this is finite. Sure, let me call this a filament. And in a ribbon, this is a finite number, finite but small number. You know? So it's somewhere in between these things. You need to work with this aspect ratio for a ribbon. You need to retain that everywhere. Yeah, just a wire. Yeah. Yeah. And the other, you want it to be small but not negligible. Okay, I won't integrate over in a ribbon. I wouldn't have integrated over the thin dimension. I'll retain the thin dimension. Okay. So these are some things I won't tell you about. Finally, I'm going to be talking mainly about statics. I'm not going to be talking about dynamics in these patterns. That's an area with a lot of open and interesting questions. I hope I can set up the dynamics questions for you if you want to think about them later. Okay, I'm going to now move away from this and start looking at basic elasticity. Okay, here's my menu, and depending on how fast you want me to go, we'll get to some distance through the menu, but I want to talk about stress and stress balance, and I want to talk about strain and stress strain, stress strain relationship. Okay? This is a little bit the opposite order in which we do basic physics. We often do kinematics first. We describe the motion, then we talk about dynamics, and then we talk about how they're related to each other. I find this just slightly more intuitive way to think. So let's talk about stresses first. I'll ask you again in about 20 minutes whether we are going too slowly. If you're going too slowly, I'll just write down the results for you. Okay, so let's start with stresses. I want to now have you think about the forces experienced by a little piece of material inside a larger piece of material. Okay? And stress is the quantity that encodes what the little piece of material is experiencing from its neighborhood. Okay? So this is a continuum theory with no scales in it. If I'm a little box of material living in here, and I feel forces from my neighbors, I can access this material in a couple of different ways. One is I can access it by external forces, gravity, for example. These forces will scale with the volume of the system. Okay? The other way I can access it is by the material everywhere around it. And that will be short-range forces through the faces of this block. Okay? These forces may be of any origin you like. Van der Waals electromagnetic of various origins. Okay? And I want you to see, if you don't know this already, is that we need lots of numbers to describe this. Okay? Because we need to describe, as we always do with force, we need to describe the description, the directions of it's a vectorial quantity, but also you need to describe where the force is acting on the object. Okay? And immediately you run into a tensorial quantity. Okay? So, I'm sorry, I'm drawing bigger and bigger versions of the same thing, but let me try and stick with this always. And I think a bigger version doesn't hurt here. So I'm going to draw an object for you that's sitting on these axes. And I want to write for you the forces that are experienced on this surface, the surface facing in the y direction. Okay? So, force on y plane. This piece of material has in front of it another piece of material which can exert on it forces normal to the surface and in this plane. Okay? So the forces are, and now I'm going to start defining pieces of the stress tensor. The simplest thing is the force normal to the plane, and you'll see I'm going to put two indices here. One index is for the direction of the force, the other index is for which plane it's acting on. Okay? So it's this. So this is times the area times y hat plus sigma zy again dx dz z hat plus sigma xy dx dz x hat. Okay? So sigma ij is a force per area in I direction on a plane with normal in j direction. Okay? Does that make this okay? So to describe all the forces on this object, I need obviously the same three quantities on the other faces of this object as well. Okay? So the units of this are force per area, which you have encountered from, which are the units of pressure, not by accident. We'll see that pressure is sitting inside this object. Yeah? So if I was to ask you, so in general, if I want to know the force in the I direction on this object, I need to add up all the sigma ij's, dsj's, so summed over the j's. Okay? And this whole object, this whole tensor is sigma x. So on the diagonals are these terms, and sigma xy, sigma xz. Okay, this is old. I think this is Cauchy. Maybe okay. So we are quite a while, quite a distance from there. Anyone knows how to pick out pressure from this? Okay, so the diagonal terms, very nice. Any further help on this? Okay, so let me ask the question a different way. So let's say I had a block of material under hydrostatic pressure. What would the stress tensor look like? If I had a little piece of volume floating under hydrostatic pressure P, what would it look like? All the diagonals are full. And that's the pressure. It's good. And these zeros. Okay? And for compressive things, we're going to put a minus sign also. Okay? So this is P times the identity, negative sign. This makes sense? Okay? So the way you get pressure, so that if I give you a general one of these, what's the prescription for the pressure? How do I get the pressure if I give you this thing? I heard the trace word somewhere. I heard a trace element saying. So I try and identify the trace of this, and I take a third of that. Okay? Is how I would do this. So can I ask something quickly? Okay, so suppose I did this. Suppose I had this, and I had just so let me say this. So so you get pressure, and generally speaking, the normal stresses. These are called normal stresses along the diagonal. Okay. And shear is off-diagonal elements. And you can see why that is true, right? The forces on a surface, say in the y direction, acting in that direction, tend to shear this object. Yeah? So something to think about briefly. So say I apply P1 this way, and I apply P2 this way. What's this under? Does the material experience any shear? Okay, this you have to think about. What I want to now emphasize is this is a tensor. This is a description of a material that you get by choosing x, y, z coordinates in the way that I've written. This object can be rotated. You can ask whether other planes feel the same state of stress or not. And this is probably something you want to work out in maybe in the half hour each we have, whether there's shear in this or not. It's got an important practical answer, and the answer is yes, it does. Along some planes, there's shear. Okay? Let's say it's a 3D object. Let's say, yeah. Let's say there's nothing coming from the other side. Okay? So let's say I'm doing this, and you're doing that. I'll leave you to work that out. Yes. I wanted to say that there is in some directions a shear, and I'd like you at some point to figure out where is the direction where there's a lot of shear and no pressure. Okay. But let's leave matrix rotation for offline. Okay. This thing, can you generate shear by looking in some plane? If you rotate this object, what do you get? If you rotate the identity matrix, what do you get? So I'd like you to think about that as well, okay? Especially the 1/3 who have seen it before, I would like them to teach it to the 2/3 who have not seen it before. Okay? I'm going to tell the equivalent set of things for strain, which are a little bit more complicated. You want to talk at all more about stress, or that basically definitions are good for you? Oh, actually, I want to talk about stress balance first. And then I'll talk about stress, about strain. Yeah? Everyone's okay with definition is okay? You understand what each of these objects means? You're getting me worried. Say something. Okay. All right. So now let's talk a little bit about stress balance. Is this a dangerous board to use? Or you can see at that size of writing, you can see what's going on? All right. Okay. So now I want to do for you force balance on this cube that I keep drawing. Okay, and I'm going to pick a small cube of size dy in this dimension, dx in this dimension, dz in this direction. Okay, and so the cube is centered on the point x, y, z. Okay. And now I'm going to ask what the equations for equilibrium are on this object. That's to say how to get force balance on this object. So you have, again, two ways of addressing this cube. One is with long-range forces that act on the bulk of this material. And then second is all that stuff. So the long-range stuff is straightforward, right? These are called body forces, and the force is just some force per volume. Okay. So the trivial example is this. Okay. That's good. Now, stresses. Okay, so let's, I'll just tell you what I'm doing and then I'll start writing down stuff, okay? I'm going to write this very crudely. We're going to do component by component. We'll do one component, that's enough, okay? So we'll do let's say forces in the y direction. It's my favorite direction. All right? So what are the forces in the y direction on this object? Which of these stresses contribute? This row, right, is what contributes. And this row contributes. One of the elements of the row contributes here, one of the elements of the row contributes from here, one contributes from here. And then there are the other three faces also. So I have to write 6 things, okay, in this brute force way of doing it, but let's be brutish for now. So there's sigma yy evaluated at x, y plus dy over 2 z, okay? So I'm evaluating it at this point on the face. And this is a force per area. And now there's the force on the other side, normal pointing the other way, sigma yy, x, y minus dy over 2, z. And these are forces per area, so I must do dx dz. Okay? Now, this is from the y pointing face. Now I'll do from the z pointing face. Sigma yz, x, y, plus dz over 2, minus sigma yz, x, y, z minus dz over 2. And then the area of that face. And if you'll just excuse me, I'm just going to write the other one and etc. Okay? You get where each of these terms is coming from? Everyone is happy? All right. All right. So you can see what's going on here, right? This is the y gradient of this. This is the z gradient of this. And this will be the x gradient of that object. Yeah. Help me. This is the force on the y face. This is the y pointing face. This one is what's acting over here. Is it okay? We're okay? And you can see that if I just do Taylor, I'll get dx, dy, dz. I'll get a volume here. And the same thing if I do Taylor expansion here, I'll get dx, dy, dz, and so on. Okay? So net force equal to 0, sum of forces on this element equal to 0 just means di sigma ij. No, I did it the other way, sorry. I did that plus fi equals 0. This is statics. Okay, this is static equilibrium of this object. Yeah, and this probably has somebody's name against it also. Actually, maybe Cauchy again wrote it in this way. If there's one person who's given you more homework than Cauchy in your lives, I don't know who it is. There is one other thing to do, do this brute force. It's easy to do, but do it. Do torque balance. Okay? Do torque balance on this cube. I'm not going to do it, but you know how to do this, right? Do talk about the center of this with all these forces. The normal forces don't give you anything, only the shear forces give you something, as you can already see. And what they'll give you is a torque balance gives you that. So this will be a symmetric tensor under torque balance. There are fancier ways of proving it's symmetric. As you can see, the actual physical thing, which is the force, only comes from divergences of this object. So you have some freedom to make it symmetric even otherwise. Okay? but this is a direct physical way of showing it. Okay, with this, try it out, okay? It'll involve writing ugly things like this, but okay, let me stop a minute. Why was I going to stop a minute? No, I shouldn't stop a minute. I should go right ahead. Let's talk about strains now. So let me ask the other question. So you said about a third of you have seen elasticity. How many of you have seen fluids? Okay, more fluids than elasticity. Huh? Okay, good. So while I'm erasing away, can somebody say what strain is? What physical quantity are you trying to get at with strain? What do you want to describe with strain? How much an object deforms is what the gentleman said. I don't know which gentleman, but okay. How much the object deforms? So let's start with material point labeled y, x, y, z. So this is some vectorial point. You do something to it and to the object, and it turns, every position in that object is changed, the position of every material point. Now, stick a label on that material point, okay? Paint an atom red. Okay? So this thing goes to some x prime, and this defines a displacement field. Okay? Now, some displacement fields are not super relevant to elasticity. So say U is a constant, then that's an object that has moved, right? I heard somebody say rigid object. So another thing that you've worked with a lot in probably classical mechanics is just rotations. And that's uninteresting also. Really, can you think about what physical quantity you care about? Why? Physical object, please. I heard vector calculus answers, which is good answer. Why do you want U to change? He said U changes the position for rotations as well. What physical quantity do you mean? What do you mean when you say something is deformed? The shape has changed, okay? Which means what has happened to material points labeled inside it? Say again? The coordinates have changed, but coordinates will change with this also. Relative coordinates have changed. Thank you. Distance between points has changed. Yeah, is everyone happy with that? So maybe somebody else said this also, but I'm hearing what I hear. Agreed? Distance between points have changed, then the object has deformed. You don't like that? If distance between individual physical points have changed, that's what a rigid body is not. Actual distances between individual material points. Is okay with you? That's what you're worried about? Okay. So let's calculate distances. Okay? So you have point A over here, and you have point B over here, and this has coordinates x. This has coordinates x plus dx, let's say. Okay, then you do something to them and they wander off in space. And I don't know, this one goes here and this one goes here. All right, and as you already have discussed, many parts of this motion may be boring. It may be rigid body motion. Right? It may not be deformation. So the question is, how much is deformation, right? So to do that, we'll try to calculate distances between these two things. Okay. So this guy has gone a distance dx. Actually, let me no, sorry, what did I do? I shouldn't have done that. That's gone a distance du. So initially, the distance between these two objects, the squared distance between these two objects, is just dx squared, right? We're okay with this? Or dxi. So I'm sorry, I'm being very rough with the algebra here. This is a building, this is a place in Bangalore in which the difference between indices upstairs and downstairs is really important. I'm just, okay? I'm just forgetting all about that. All right? So now I'm trying to ask, what's the distance? So this is dl, okay? And this is dl prime. I'm trying to ask what this distance is. So it is as somebody up front said that what is now important is whether u has a gradient to it. If u has no gradient to it, then you're still at the same separation. So u must have spatial gradients. And as you can see, what's going on here is this is dxi prime, dxi prime. So this is dxi. So go back here. Squared. Okay, and now I will again, do this whole thing out in painful detail. Okay. Okay, we're okay with this. This is all the things you can get from this. Okay. Okay. And this part obviously is what's contributing to the strain. These are all the changes. And you can see all of them have gradients of u in it. So I'm going to write this as again as this is again one of those twos that needn't have been here, but is here for simplifications later. What is this object epsilon ij? This is this term. I'm going to make this term look symmetric, okay? I'm going to switch between I and j for one of the twos, and for the other, I'm going to leave it like this. So I'm going to say dui dxj plus duj dxi. And then there's this piece. Again, I would like to have instead of these indices I've summed over, I want this to be dxi and dxj. So I'm do a little bit of index swapping over there, and I'll get so if you have done fluids, you will have seen some of this before. And in particular, you would have seen this piece. Okay, I want to make a couple of comments. First thing is this is by construction symmetric. And at some level, you should have seen this coming because you're constructing it from a distance. Okay? That's right. That's right. That's right. So both of these are, this is a completely symmetric matrix. Now, one thing I wanted to tell you is this piece, this is actually often referred to, I think, as the Cauchy strain. And I think this whole thing, I don't know, goes by the name green. This is that same old green. It took a couple of centuries to get to this in a nice way, and that this piece was promptly dropped. But I want to particularly draw your attention to this piece. This piece is to the same order in this calculation, but this piece involves, it's not linear in displacement. Okay? So if you exclude this piece, elasticity is a largely, you can get away with linear, you get a theory that's linear in displacements. But what I want to point out to you is that this piece can be quite important. This is a slope, right, roughly speaking. In distance, yeah. It's order dxi, dxj, but it's got two pieces of slope in it. It's not to the same order in slope. Okay? So I want to particularly tell you why this piece is, this raises the level of complexity a lot. We'll bypass some of that complexity, but I want you to see where it comes from. This object, as I turn it around, can be completely within linear small strains internally, but slopes can be big. The deformations here can be comparable to the size of the object. So for a lot of what will be necessary for this, it's important to retain this piece. Okay, how am I doing on time? I'm doing terribly on time. Okay. Okay, so I had a few little exercises for you to think about, essentially similar things as you had before. In the stress case, I wanted to ask about simple cases of strain and ask whether they were shear strain or whether it was getting extended or compressed. But I'm actually going to skip that, and now I'm going to talk about very quickly. I'm down to 5 minutes, right? I'm down to 5 minutes, no? Oh, much better, much better. I was in high state of panic. Okay, all right, okay. Thank you. So the things I'd like you to think about, just, I mean, this is just to make sure you understand definitions and things. Please think about this object, and if you make it that size, please figure out what is U, what is epsilon. If you take an object that's like this, that's a square, and you turn it into a parallelogram, please ask yourself what is U, what is epsilon. Okay? This will take you all of 5 minutes, I think. Small thing I did want to say is this is symmetric, we said. So it's symmetric, everything is real, it's diagonalizable. If you diagonalize this, and you get it looks like this, with zeros in here. These things are called the principal strains. The corresponding objects in the stress is called principal stresses. So you realize that no matter what you do, if this is diagonalizable, that means you can find directions in which there is only normal strains. Okay? You can draw as complicated an object as you want, but the fact that you have a symmetric tensor says that you can always find such axes. Another useful thing is, since we figured out that these have to do with length, you can ask under some general strain, how does volume transform? Okay, so if you had a volume element that was dx, dy, dz, then this thing makes it particularly convenient for you. This diagonal form makes it particularly convenient for you to figure out new volume. It's these three lengths multiplied, which is dv times 1 plus epsilon 1, 1 plus epsilon 2, 1 plus epsilon 3, etc., which, if the strains are somewhat small, is just 1 plus the trace of epsilon ij. So this is, I want to talk about now the relationship between stress and strain. The simplest form, all of you have seen it, is Hooke's law. I'm going to write Hooke's law in slightly more complicated form for you, because obviously we have 9 quantities to deal with. Though, as you know already, it's not 9, it's 6. These are all diagonal objects. These are all symmetric objects. Okay. All right. And like the Hooke's law, you know, this is a linear relationship between stress and strain. I will do this quickly in 2 ways. I will do it in 10 minutes in a workman-like engineering way, the way I learned it, which gives you some, I think, physical intuition. But for a minute, to watch me pretending to be a theorist, and I'll do it the quick way. So you have this object, and you want to write a relationship that's rotationally invariant with this object. So you have 2 symmetric tensors. You want to write a rotationally invariant relationship between these 2 things. How do I do this? But I need no. Okay, what's a simple thing I can do between these 2 things? I can put a scalar, right? Okay, a scalar will make you happy. I can make them simply proportional, but I also can use identity matrix on the other side. Yeah, these are the 2 things I can do, so this is precisely what I will do. I'm going to say some constant. This constant depends on the material. Here's another linear thing I can do, which is a linear thing I can construct from this is trace of epsilon. Okay, and this is it. This is Hooke's law, and I'll make it more physically apparent by doing it in the pedestrian way soon. But these are material constants. They're called the Lamé constants. We will see Mr. Lamé again. But we've moved along in the years a little bit, but I have this here, okay? Yeah, so just brutally, explicitly, let me write out one just so that you... So, does this look like your Hooke's law anymore? As I write it out, probably all your... So same thing for all the diagonals, and then for the off diagonal, let me write. And then nothing from there, right? So the resemblance to Hooke's law is probably rapidly receding in your heads. I want to reconnect and make it look like Hooke's law again. Yeah, please. Related to. So the gentleman here is asking, is this related to Young's modulus or not? And the answer is yes. We'll write it out explicitly, the relationship to Young's modulus. Okay? All right, so this is, I promise you that this is Hooke's law, and it's going to look like Hooke's law in a slightly different way quite soon. So, and then the same for all the shear components. All right? So this is the first time we've talked about what the material is made up of, right? This is material property, these things. Okay? So 2 material properties for an isotropic material. Somebody said something about higher order constructions. You said something about higher. Yes, and so if you take materials that are not isotropic, then you can get sudden explosion of material properties that are important. The proportionality constant between this and this is a 4th order tensor, and there are as many as you want material constants as you want to play with. Okay, let me go back to something that looks a little bit more like Hooke's law. Let's take I mean, look, in spirit it's Hooke's law, right? This is stress is proportional to strain, right? Let me consider a simple state of stress. Let's take an object and let's just pull in this direction. This is the kind of thing you do when you say F equal to K times X. Okay? That's Z direction. Okay. So sigma ZZ is whatever force I'm pulling with in the Z direction divided by area. Okay? So this is just from Hooke's law. This is the displacement in that thing, area. And I don't know, let me give this thing a length also. Then this is KL over area. I'm going to take UZ and divide by L. So this is UZ at the length of the object. And you can see that this is Young's modulus. And this is... It's okay? I've used... This is... sorry, what I've used is Hooke's law. This is your F equal to Kx. Yeah? And this is Young's modulus. Units are? Units are? Units of Young's modulus are? Okay. Say again? Same as stress, yeah. Newton per meter square, yeah. So Newton per meter square, or if you like it, Pascal, same as stress. Something that's nice to keep in the back of your mind is this. So this is force per area. Something that's useful to keep in the back of your mind, and it's not a complete coincidence, that this is also units of energy per volume. Okay? That has the same units, and that's a useful physical thing to keep at the back of your head because we'll use it. Okay, so the thing I want to tell you, the bad news here is that when you do this, and you pull an object this way, you get strain in the z direction, but that's not all you get. Okay? When you do this, you get compressions in the other directions. So, or if I do this gently, the object doesn't just elongate in this direction, the object can change dimensions in the other orthogonal directions also. So this thing typically becomes thinner, typically though not necessarily becomes thinner. And you get strains in the other directions. So the strains in the other directions are, maybe I'll write it here, sorry to go backwards, but you get epsilon xx, which better be equal to epsilon yy. If there's a strain in the other direction, it shouldn't know which, it shouldn't select a plane. But this is a proportionality constant. Okay. And this one is called the Poisson ratio. If we were really going to go into elasticity now, what I would tell you is what the physical limits are on Poisson ratio. I would show you that some of these quantities better be positive and that there are limits on this, but I'm not going to go there. But you can see the sort of two material quantities again for an isotropic object. I have this and this. Let me put these together and write them out for a little bit for you. So if I'm to write a relationship, yes. If the object is isotropic and I'm pulling this way, I shouldn't be able to select a direction in this plane. So whatever happens there must happen here also. Yeah? If the object is not isotropic, if the interior elastic properties of the object are anisotropic fundamentally, then everything gets a lot more complicated. Okay? But I'm talking about, yeah. Yeah, yes. So it's that quantity that stays the same. The actual deformation depends on whether you're thin in this direction or fat in that direction. So I'm not saying the shape of the object is isotropic. I'm saying the material properties are isotropic. Make sense? Yeah, so I can't say that I got wider by 1 centimeter this way, so I must have got wider by that. That depends on how fat I was to start off with. Okay, so if I'm getting a strain in this direction, it can come from two things. It can come because I got pulled that direction, or it can happen because the other directions did something to me as well. Okay, you can be completely stress-free in one direction, but your dimensions can change because something happened in another direction. I won't write down these, okay, but you can write them down. All right. The relationship for shear stresses look easier. You need a shear stress in that direction. I'm not going to work this out for you. It's actually not bad to work out at all. Think about something that does this. Okay, so I have a stress this direction, a compressive stress this direction. And let me say I'm extending in this direction. I drew these arrows very particularly this way. The reason is this is a particularly interesting situation. This is going to turn out to be pure shear. And the way you will do it is just think about equilibrium along here. And you'll be able to derive this from what I've given you about the other directions. All right? So I'm sorry, this is a much uglier way of writing things, but it's a little bit, see, that was so pleasant but opaque, ugly but transparent. So it's good to know both when you read books. So this description is completely equivalent to this description. And somebody, you had asked maybe what the relation is between Young's modulus and this is. I can write them out, but okay, you've got 6 linear equations there, you've got 6 linear equations there. You can please change variables and get the answers. It's not a particularly enlightening or amusing job. Let me just write the answers, okay? So E equals mu times 3 lambda plus 2 mu lambda plus mu lambda equal to and then you there's version. I'll put the version in the notes that flips it the other way. Okay, so this is all we need to know of bulk 3D elasticity. Okay, and now I'm going to take away one dimension. That's my next game. Okay. So let me, since I'm actually okay, good. I'm not as far behind as I was worried. The third who have seen elasticity have seen all of this? Yes. Okay. Yes, please. Yes. No, these are all, everything here is an intensive quantity. This is all material properties, local material properties. They had nothing to do with so the scale, shape, size comes back in the boundary conditions of how you specify the problem. Everything here is as a local quantity. Okay? Okay. Before we move on to next thing, which is reducing to 2 dimensions. So you'll get to know the 3 of us slowly, I think, over the next 5 days. But I want to get to ask a little bit about you. How many people here are experimentalists? Okay, not bad. Okay. It could have been worse, but fight the good fight. Okay. Okay. So in everything that we've been dealing with, this is a material property at a coarse grain scale that's much bigger than the smallest scale in the object. In something like this, that scale is the atomic scale. In something like this, which has macroscopic pores in it, if you measure this quantity very locally, you will get the modulus of air. So here you need to coarse grain at a scale that's bigger than the smallest hole in this form, for example. So, as I said in the beginning, this is a completely microscopic theory. There is no smallest or biggest length scale in the problem. The big length scales are boundaries. The small length scale is something that is dependent on your problem. Okay. If you're working with, I don't know, some complicated biological material, that's probably, you may have to coarse grain over microns. If you decide you want to write elasticity for this thing, then you have to go to a scale that's bigger than the small objects in this. You can write local elasticity for the paper itself. Okay. Yeah, you choose what battles you want to fight. I mean, so a lot of these were developed by engineers. So, for example, there's a whole class of theories of elasticity going after Coursera. And Coursera developed continuum elasticity when they were building, I've been told this, Eiffel Tower. So your scale there is a mechanism. And you have to be bigger than a set of struts. So you can, the small scale in your problem may be a meter. So I think that's the idea. Pick the small scale in your problem, coarse grain above that, and then go from there, okay? Okay. Now I'm going to talk to you a little bit about thin plates. We erased what the meaning of thin was, but let me try and put that back on. So I'm going to think about an object that's looks like this, let's say. And the definition of thin is T very, very much smaller than W, which are the in-plane dimensions. Okay? And I want to tell you that this geometric definition has some real mechanical meaning as well. So the idea here is, I really don't care in what I'm going to develop in the next 10 minutes and use for the next 2 or 3 days, what's going on through the thickness of a piece of material. I don't want to know whether the middle of a thin sheet is experiencing a very different force or displacement than the top bit, you know. I just want to know about how. You get the point? This is my thin material. I don't want to know how page 24 behaves differently from page 25. I want to know the overall shape of this. So I don't care about what happens through the thickness of this. So I'm going to now take 3D elasticity and integrate it across this thin dimension. That's the immediate plan. And obviously you will inherit some things. You're making this out of a material. This is a bad example because it's got pieces of paper in it. But if I was doing thin sheet elasticity for this, there are many, many scales above the atomic over here. But I don't care about those. I'm going to integrate through that thickness now. Okay. So I want to show something that's a little bit obvious and maybe intuitive to you. If I take something like this, there are 2 ways in which I can deform it. One is I can change the in-plane distance between 2 points on this. Okay? It's very hard to do that with paper. But if I had a rubber glove or something, I could stretch it this direction, and then I change the in-plane distance between points. The other thing I can do, the other fundamentally different mode of deformation is this. So here, to some order which we will talk about in more detail, the distances along the piece of paper between individual points doesn't change, and yet there is deformation. Okay? So I want to try and deal with these 2 separately, and I want to start from where we started off, the starting point that we had earlier, and develop what it takes to make these 2 kinds of deformation. Okay, so here's this object, And the first thing I'm going to do is, okay. I'm going to try and stretch or compress this, okay? So let me pull it this way. This just in the y direction. And this thing has, has dimensions like that. Let's give it a length also. So this is something we just did, right? So epsilon yy, if there's no forces in this direction, is just sigma yy divided by Young's modulus. Let me say a word or two now about the forces I'm applying here. Let's say I apply some net force along this surface. But now maybe I don't care about how that force is distributed along here. Does that say 5 minutes or does that say I'm done? That says I have 5 minutes, okay. Let me not care about how that force is distributed along this face. That's to say whether the force is biggest in the middle and less on both sides or whether it's uniform force. Let me just take a force per line, okay? Then this is something like this, okay? I'm going to call this something different now. This is force per line, and I'm now going to call this a two-dimensional stress. Okay? And I'm going to say, okay. So remember, stresses earlier were forces per area. In 2D, I'm going to integrate that stress across the thickness. Okay, and I'm going to give you forces per line on the surface. And this thing is what it takes to stretch a material. And this thing is called the stretching modulus. Okay. Sorry, this is called Y, even though Y should be reserved for Young's modulus, but that's the way it is. Now let me do the other. So this was stretch. Let me do bend. Okay. So I have a material that looks like this, bent like this. All right. And again, if you choose, this is Y, Z. Okay. So the thing I wanted to say is, let's give it some deviation from the flat shape. So let's say the deviation is, what is the symbol? I don't know. I draw it because you can draw an uncontrolled number of wiggles. Okay. So the thing I want to understand is, bending won't couple linearly with this. So there'll be no side term for this. Right? I can move the sheet up and down with no penalty. There's also nothing to do with slope. I can do this. The first term in which bending actually costs force or energy is in curving the material. Okay? So if I'm trying to ask how much energy or force this takes, it's nothing until I start having second derivatives there. Probably the one thing I should have written down here also is, from this I need to get, let me start writing energies as well. Energy per area is half Y. Shall I work that out or will you work that out? This is just going from F equal to Kx to E equal to half Kx squared. Okay. So if I'm trying to write energies or forces, it's difficult. So next thing is, so energies will not depend on this, will not depend on this, will depend on this, but it's indifferent to the sign. That's to say, this takes the same energy as this. Yeah? So you need something, if I'm to find energy per area, you need something that's quadratic in the second derivative, in the curvature. And the coefficient that goes behind it is called the bending modulus. We'll work through bending modulus a little bit more physically in a second. In a second that we don't have. Let's start with that next time. But one thing you can work out is immediately dimensions. So what's the dimensions of B? So this is energy per area. Say again, this is energy per area. What's the dimensions of this thing? 1 by length. So this is 1 by length squared. And this is energy per length squared. So this is energy. B has dimensions of, this is energy. So what's the dimensions of B? So B depends, something to do with the material, the thickness. You agree? If I choose a stiffer material or a thicker piece of material, it's going to change. So dimensionally, what is this? What's the dimensions of this? This is energy. What's the dimension of Young's modulus? Force by area or energy by volume. So what must this look like? It's cubed. This is thickness cubed. We'll work this out from a little bit better tomorrow. But the thing I want you to immediately realize is, of course, to compare EB and ES is a little bit more we have to do, but this is something like ET cubed. And let's see, in the worst case, if I go this way, it's like, this curvature is almost the size of the piece of paper. So this is very big curvature, and this thing is ET. Okay? So the ratios of these are so to bend something quite a bit is incredibly easy. And it's incredibly easy by the same ratio as we wrote for just geometrically. So the ratio of bending energy density and stretching energy density in a material typically is like the aspect ratio, the geometrical aspect ratio squared. And it doesn't depend on the material property. Actually, it does very weakly, and we'll fix that tomorrow. Okay? So we'll soon now be able to realize that you can separate scales here. There are two kinds of deformations in this object, but they cost vastly different amounts of energy. We'll use that a lot. Okay, thanks.
Questions? Okay, so then we meet in the tutorial at 4:30.